Hello. Hi, I'm going to just send you the YouTube link now.
I think Carol just sent it in there a second ago.
Ah, perfect. Okay, that'll do. Alright, I'm going to get out of Teams here because it messes up with my everything else. So, goodbye. Okay, so welcome to today's tutorial, CS320. Today we're going to start moving over to the network layer. So now I should be uploading the lectures for this in the next, I hope tomorrow anyway. So we will just go ahead of the lectures in this tutorial. And today we're going to focus on So this is, remember where we are. So we're if we go down the stack, we started out up here at the application layer. At the application layer, then our messages. We started off with a message here, say. This is our message, we'll say. Then that message was passed down to the transport layer. And this message was bundled inside a segment. So here's our message, and some new information added to that segment, some header information like port numbers and that kind of stuff, checksum and so on, which we've all learned about. Now, this is going to get passed down to the next layer we're going to work on. It's really our second last layer, the network layer. We end up with the new thing here. Maybe I should just define the old one first. So this was our segment. This is our segment. And then things like port numbers or multiplexing and so on. Here we're going to package our segment here. Which has our message encapsulated inside it. We're going to encapsulate that entire thing into something new, which we'll call a datagram. This is our IP. And later this will be encapsulated into something else, our link layer packet, like our Ethernet packet or our 802.11 packet or whatever. But right now we're going to focus on the network layer. So we're going to focus on this packet, and it's called a datagram. How's that coming out on the screen? Is it okay to read? If you have any feedback here, guys, just shout out. Okay. And today we're going to look at routing algorithms. In this tutorial, or in this flipped lecture, or whatever you want to call it, we're going to go through how routing happens, and then I'll show you some exam questions that ask about routing algorithms. Okay, so we're going to take this datagram here. We're going to see how does this datagram work. So the datagram, in the datagram, we have a source IP address, and a destination IP address. So the destination IP address, just like your postal, this is a little bit like an envelope system, your Christmas card. You might have your sender's address on the back. Some people do that. And you'd certainly have the destination on the front, the postman or woman to read. The diagram is the same with the destination address here and with the source IP address. The interesting thing about the destination source IP address is, at least for version 4, I can give this example, which is the more common version. It looks like the destination IP address. It looks like this. It looks like something like 192.111.103.200 or whatever. So this address, um, this address is a little bit like postal address. So this is a little bit like the bottom of your postal address, the country code, if you like. So the deeper you go into it, from right to the broader the address. So this is like going from the bottom up of the postal address, if that makes sense. So this sort of you're closing in on your destination to get to here. This would be a broader part of the destination code over here. So it is hierarchical. Just like a postal address. And it's this address here and the way it's structured that allows routing algorithms to work. And that's what we're going to look at. We're going to look at some examples of routing algorithms. In particular, we're going to look at Dijkstra's algorithm today, and maybe in the second hour we'll look at the Bellman-Ford distance vector algorithm as well. So there's two big algorithms that are used for routing based on these IP addresses. And it's not just the IP address. The IP address tells us where to go, but it's also the costs of the links between the IP address, the different routers with different IP addresses, that governs the path that is determined by these algorithms. So I'm going to go to the notes briefly, go through Dijkstra's algorithm briefly, and then we'll look at some examples of what it is. Okay, so you should be able to see a slide here showing the idea of a per router control plane. So control plane relates to this routing process. So how is the route controlled? Hence control plane. So inside every single, so there's two different ways to do this, and the most common way, historically at least, is per router control plane. So in other words, the router itself. So each and every router has a routing algorithm that runs independently of all the other routing algorithms in all the other routers. The purpose of this routing algorithm is to figure out what is the best path for a particular that has arrived at the router. So in other words, what outgoing link should this router send that data on, based only on its destination address. So the routing algorithm figures that out. Now it doesn't do it completely alone. It talks to the other routers in order to determine what are the link costs between the routers. And that means it needs to know a little bit of information about how expensive these paths are. What are their bandwidths? You know, they may be congested, for example. They may have long delays associated with them. So what are these costs? So this cost information of the links is exchanged between the different routers, and that then is used to as the parameters input to this routing algorithm, which determines what is the best path to send a particular destination address to. Alright, I'm going to jump forward, having just done that little preamble. I'm going to jump forward to the algorithms of interest. Here we go. So, okay, so what is a routing protocol goal? The goal is to determine a good path. That's what it's about. That word good, I mean, what does it mean? It could mean a few different things. It could be the fastest, the least congested, the shortest delay, or the least expensive, maybe financially. So there could be different costs associated with a particular link. And this is a big problem in computer science. So I'm going to jump straight into it at the deep end here. So we're going to look at our Dijkstra's algorithm first. Routing algorithm, which is often implemented on these routers using a graph theory here. So this is a simple graph of a small network with 6 nodes. So N is for nodes or routers, which have been given the names U, V, W, X, Y, Z in this example. And then you'll notice that there are several different links here, more than just 6, that connect these routers together. So I've written them here based on their names. So based on the names of the routers, for example, UV is this link here, and so on and so on. Each link has a particular cost, and as I said, that cost could be the delay associated with sending something on that link, or the bandwidth, or it could be some financial cost, or it could be several other types of costs as well. So we're going to base everything on this graph. In fact, we're going to base both of the algorithms we're going to learn about on this graph. Right, so our cost we'll call C. So we'll use this notation C between node X and X dash, or router X and router X dash. That's the cost, whatever it may be, whatever that might mean. So the cost of a total path would be the sum of the costs of the individual paths that make up the sequence. So the question then is, what is the least cost path between 2 nodes? Let's take this example, U and Z over here. Well, I can quickly look at it and think, okay, it's U, X, Y, Z. That path there, it's clear to me, just visually, I can do it very quickly in my mind that's a cost of 4, and I can't see anything else that's faster. But I mean, that was a simple case with just 6 routers. What if you had hundreds of routers? Then it becomes, or even thousands of routers, then it becomes much more complicated. And I can't do it in my head anymore, so I need an algorithm to do it for me. Now we're going to talk about routers algorithm. I'm just going to jump straight into it now, and I have much more information when I do these in the lectures, so you can go back over the videos I put up if you want to know more about this stuff. So the first one I'm going to look at is the link state algorithm here. We're going to go through a few examples, and then we are going to do some exam questions based on it. This is called Dijkstra's algorithm, named after the inventor of the algorithm, Dijkstra. Again, it's based on net topology, link costs, etc., etc. Here's the notation again. CXY is the cost from node X to Y. DV is a new one. This is the value of the cost of the path from source to V. So this is our current cost, if you like. PV is the predecessor, and N dash is the set of nodes that we know everything about. Now this won't mean much to you just yet. It will as I go through an example. So let's jump into it now. So there's the algorithm again. I'm not going to read this because it's just kind of it's code almost. So it's kind of hard to read. So let's just go through the example, and then the code will make more sense. Right. So here's our graph down here, our network topology. You can see, so we're trying in this case to get the least cost path from U over here. Hence, we'll see U is the first node we know everything about. So we're getting from the path U, the router U here, all the way over to the right side to router Z. What is the least cost path in this example? Not as easy as the first one I showed you. You kind of have to explore a few options here in order to get the path visually. But let's see how you do it using an algorithm like Dijkstra's algorithm. So step one is to write down the cost to the routers that are connected to you, to node U. So there's three. You'll notice down here there are three routers connected: X, W, and V. And those are the only routers I can know anything about in my first iteration here. So X, W, and V, and they are connected by three separate links here with cost 537. So what I do is I write down under V, W, and X here, I write down 7. The cost to get to V is 7, and the link that preceded that journey was U. So the link immediately before it was U, which was obviously the first one. It's kind of it's a bit easy for the first iteration. The cost to W was 3 on this link here, and the link immediately preceding it was U. Again, so 3U. And finally, X here. The cost to get to X is 5, and the node preceding it was U. The other two nodes here, Y and Z, were not directly connected to U here. So therefore, we just write down infinity. The cost to get to them is not known, so we'll write down infinity. Now, at this point, we look across the everything we know about in this iteration, and we see that the least cost path of all of them was this one here, 3U. So 3 was the smallest number. So we'll add this node here, W, to the list of nodes we know everything about. And we move on to the next step. So this time, I write now, using this information that I have, I'm going to write down any new information I can derive based on this new least cost path I've just figured out to W here via U. So I've just learned that W is, to get to W, this is the definite best path. So what about if I just take W and I explore the other paths? So what about getting to W up to X? Well, that's going to cost me 4. And my previous cost to get to W was 3. So that's 7. So 7 to get to X via W. Is that better than what I already had? Let's check out X over here. Well, X was 5U, and now I'm about to write down 7 via W. 7W is not better than 5U. 7 is not better than 5. So therefore I leave 5U alone there. And I put 5U, write it down again. Let's go for V this time. So V is the one down here. So the cost to get to V via W is 3. And we know that the cost to get there in the first place was 3 here. So the total cost therefore is 6. So 6V, is that better than what 6 via W, is that better than what I have over here for V? Yeah, so 7 via U is not as good as 6 via W, so I'll replace that. I'll just write down 6W here. Obviously I just did that one. What about this now? Yeah, so a new one is opened up here. Y is now connected. So the cost to get to Y here is 8 plus the 3 is 11. That's definitely better than infinity, so I'll write down 11 via W. And I'm still not connected to Z. So now I look across these three numbers here and I ask which is the best, and it's clearly 5. So I circle that one, add X to the list of things I know about, and start again. So now I go to X. The cost to get to X is 5, as you can see here. So I'm going to add 5 to everything else. So where's X? Here we are. Okay, so what about to get to W? That's going to get 4, it's going to be 9. That's not going to be any good. So you can see W is already circled. We don't need to look at that. We know that the best route is 3. What about Y over here? It's going to cost 7. 7 to our 5 is 12. 12 is not going to be better than... okay, so we now know enough to do, and it's important to note that this is all using the IP address in the first place. So the IP address is telling us where we want to go, and then the routing algorithm is telling us the best path to get there. 5, 3, 5, 1, 2, 2 and 3. And there's one more down here, 1. Alright, so the question is, can we figure out the least cost paths here using Dijkstra's algorithm? So again, it's an iterative algorithm. So we'll write down our table. So we'll start off with our table here. The number of steps that are going to exist here will be equal to the number of nodes that exist here. So the number of routers. So I'm going to have 6 iterations here. And yeah, so this will be my step here. There's going to be 6 iterations. I know that because there's 6 nodes. I'm going to call it, it's going to start off with 0, because in 0 we don't really do anything. 4, 5, and 6 down here. Oops, sorry, 5 is the end. Started at 0. And what are the things? So n is the list of things I know about. And dash here. And then I've got the list of nodes that I want to know the least cost paths to. 1, 2, 3, 4, and 5. I only need 5 in this case because there's only 5 other nodes. So we're looking at the least cost path here. From you to all nodes. And this is Dijkstra's algorithm. We'll look at another way to do this in a minute. Also known as the link state. It's a form of link state algorithm. Okay, so let's put it. So what is in here is the cost to get to V, the cost to get to W, the cost to get to X, the cost to get to Y, and the cost to get to Z. And then the P is the previous node. The previous node on the path to V. Previous node on the path. Previous node. Previous node. Previous node. Okay, let's put in the information here. Right, so we start off at in iteration 1. What do we know about? Well, we're starting at U here. So we're starting at U. So at iteration 1, we know U. We just know about U. That's the only node we actually know about here. So I'll put U in here. The previous node, to get to V. Let's look at V. So we can only put in information here about what we're directly connected to. So U is directly connected to V, X, and W. So we can go to V here and we can put down the cost to get to V is 2 via U. Cost to get to W is 5 via U. And the cost to get to X is 1 via U. And everything else we put down is infinity. Is everybody still with me? I have no idea if everyone's watching this or not because I'm not here. Audio is hard to hear. Really? Guys, can you confirm you can hear me or not? Hello? Can anybody hear me? Can anybody hear me? Hello? Hello? Can anybody hear me? Hello? Okay, so I think it's coming back now. Okay.